Hi, in this video, we're going to take a look at generalized estimation equations, and we're going to be using geepack from R to do this. Okay, so the idea here is that I'm going to be having repeated measurements on something. Maybe it might be like a town, it could be a location, it could be a person. I've got repeated measurements somewhere. We're going to call whatever those repeated measurements groups are going to be our clusters. And so if I measure the same person multiple times, all of those measurements for that one person are in the same cluster. So each person corresponds to a cluster for that situation. Or we could have a location correspond to a cluster. However we work out, it's a label. From a math perspective, we really don't care. All right, so when we do this kind of stuff, we would anticipate that we're going to have some correlation going on, right? You know, if I measure the same person multiple times, probably a correlation between them. And so when I do my model fitting, I want to take that structure into account. And so we'll use generalized estimating equations to do this. All right, so what we're going to be doing, we're going to be using generalized estimation equations to fit marginal generalized linear models to clustered data. So clustered, think same person, multiple measurements. And this is a robust method to fitting models. And so this will, this is very advantageous compared to just the regular out of the box way. Cluster data can arise in a lot of situations, such as longitudinal data and repeated measures. So the generalized estimation equation approach focuses on models for the mean of the correlated observations within clusters without fully specifying the joint distribution of the observations. And so what we're doing, we're basically specifying as little as possible to be able to fit the model. All right, so what type of correlation structures can we get? All right, well, we're going to be able to get independence, exchangeability, autoregressive, unstructured, and user-defined. All right, so in independence, if we choose this parameter in R, we're going to have zero covariance between observations within the cluster, and we'll have constant variance within the cluster. All right, so the covariance matrix within the cluster is a constant diagonal matrix. Now, exchangeability, here we have constant covariance between observations within the cluster, and we have constant variance within the cluster. Okay, so here our covariance matrix but within the cluster is going to have a constant value off the diagonal and a potentially different constant value on the diagonal. Now for autoregressive, well, in AR1, we're going to say that we have geometric decay of the covariance between observations in the cluster. All right, so what I'm saying here is that each time we get, we have a first observation, second observation, third, the bigger the gap between observations, the covariance degrades by the same multiplication amount. And so I'm going to call it geometric decay for the autoregressive one. And we're going to have constant variance within the cluster. And so we're going to have two parameters for our covariance matrix. We'll have the variance along the diagonal, and then we're going to have that the decay term, where the covariance between first and second observations, or second and third, third and fourth, so on, is the variance times that coefficient of decay, and then the amount of covariance between first and third is going to be the same as we had before, but we're going to multiply by that same decay coefficient a second time. Will be squaring the decay coefficient times the variance, and then so on. It will keep on growing geometrically for the power that is. Then unstructured, here, this is the wild, wild west. Here, we have different parameters for every single covariance, and we have different parameters for every single variance. And so this is the most flexible by far, but there's a problem with this, is that this can be computationally intense can be, very heavy lifting. My laptop that I'm using right now to film wouldn't even run it on the example that I'm going to give you. I had to comment out the code. It just said it takes too much memory to do it. It threw an error. So warning, unstructured correlation structure, it should only be used with great care. It may cause R to crash. I copied and pasted that directly from the help documentation. And then there's user defined, where we can go in and we can specify what the correlation structure is going to be. All right, so let's go ahead and set up some examples. So we're going to be using piping because I always like using piping. I'm going to suppress number of digits so I don't get blasted in the face with them. Avoid scientific notation. Clear my workspace of any junk that I've had before. Now let's go ahead and use the SA Heart for coronary heart disease data set from the Elementary Statistics Learn package. Now, it's an old package. This is how you would download the package if that version of the package does not agree with your version of R. This is a good way to override that. And let's go ahead and do a light data prep of converting family history to dummy variables. And here I'm just switching coronary heart disease to more explicit labels. I like doing that when I'm going through and going to be, doing my data visualizations. Instead of having 0 and 1, I like to say heart disease explicitly, no heart disease explicitly. All right, so let's go ahead and fit our baseline model. So I'm going to use age, type A personality, tobacco, cholesterol, and family history as my predictor variables for coronary heart disease. And so this is just standard generalized linear models, just so that we have something to, compare to. And, so we get the results. I've fitted this model tons of times in this video series. All right, so now let's go ahead and use generalized estimation equations. The data are assumed to be sorted so that the observations on each cluster appear as contiguous rows in the data. And so if one person is getting measured multiple times, we assume that how this is structured is that those rows are all stacked on top of each other. And so I don't have like person one is here in the data set and down here also. They need to be adjacent rows. I'm not going to use actual cluster data for this. I'm just going to run things just so that we can see how they work. But this is just something to be mindful of. So if the data is not sorted the right way, we can end up having problems, and we will have problems. All right, so let's go ahead and fit just the same model that I had before, same formula, and I'm just using default settings on everything. geepack, here's my data, and here is, now here, I just said that I want, just so that I could have something as clustered, I went ahead and just said family history, which doesn't make sense, but I just want, this will pick up like a contrast maybe, and so we can see that we get age of 0.05, 0.05, intercept of -6, type A of 0.038, pretty close. So the values are pretty similar to each other across the board. A little bit of a difference in tobacco and cholesterol, like that. And you'll notice that I don't actually have actual family history. So that disappeared from the coefficients estimated. And so that, so here, and we can pull the coefficients using the coefficient function, this method. We can do a summary to be able to do our Waltz test for hypothesis testing. And here is, we can pull just the coefficient portion of the summary output so that it's a little bit easier to run our hypothesis testing, and we can get our variance covariance out of here. And now the plot function just plots the residuals in response to the predicted value, and we can just see what's going on. Here, remember that we're really looking for the extreme values when we look at the residuals because we don't have the distribution assumption we have with simple linear regression. Now we can extract the fitted values using the predict function, just like with regular generalized linear models. And the residual function will give us the residuals. And so we can, here I put into a data frame so that we're able to go ahead and just see it a little. I like to color my, my points by an important variable. Target variable is by far the most important. Now running ANOVA, you'll notice that it doesn't actually run ANOVA because we don't have the same distribution assumptions. It uses the chi-square distribution to run our hypothesis testing. And so we've got age, type A, tobacco, cholesterol, and we can see that we might want to consider getting rid of cholesterol. Now this is a junk model because the clusters don't make sense. I'm just running the code to show you how you could do it. All right, so now let's talk about adjusting for correlation structure once again. All right, so these are the ones that are permitted. Here are the different parameter values I can give, like independence, exchangeability, autoregressive, unstructured, and user-defined. All right, with independence, here we have independence between observations within the cluster, and we have constant variance within the cluster. Our covariance matrix under independence is a constant diagonal matrix, and that's within the cluster. The exchangeability, here we have constant covariance between observations within the cluster and constant variance within the cluster. Okay, so our covariance matrix here, we have constant off-diagonal values, and we have constant on the diagonal. And so there's two parameters of the covariance matrix. In independence, we just have one because we have 0 for the covariance. Now, AR1, autoregressive 1, we have that geometric decay of the covariance off the diagonal. So we have a variance estimation along the diagonal, and then every time I go one off, above or below off the diagonal, the value decreases by a multiplication of by a parameter. Then unstructured, this is the wild, wild west of covariance for this, that we could have a different covariance between first observation, second, different covariance between first and third, different covariance between first and fourth, different covariance between second and third, different covariance between second and fourth, different covariance between third and fourth. All the entries of the covariance matrix can vary on this one. And so here, there's this is very flexible, but there's no theoretical structure to help the system fit the model. And so this can be computationally very heavy. I tried to run this on a relatively small data set, and I just got an error, unable to allocate the sufficient memory for it. So we don't want to use this unless we really feel it's important for our modeling structure. All right, and so here we'll just run through the different examples. So we can do correlation structure of independence. I'm just modifying this aspect to it. We can see we get our coefficients like we did. Now for autoregressive, you can see that we all, in addition, so notice I've got regular things coming out for just like formula, coefficients, degrees of freedom, then estimated scale parameter, and that's the big stuff. When I get down here, I have the same thing until I get down to the estimated correlation parameter. Here now I have the decay aspect to it, in addition to the estimated scale parameter. So here this is on the diagonal, and every time I go off the diagonal, the off-diagonal value decreases by being multiplied by 0.0152. Now exchangeable, here once again we have the covariance aspect. We have the covariance matrix has this on the diagonal, so this is my variance estimate, and then I have a constant covariance off the diagonal. And so all of those entries are going to be this value times that value. Now, unstructured didn't work. I got an error, memory didn't work out for me. I commented out the code so you can see how I tried to use it. The code was running. It said insufficient memory to run it. It's a relatively small data set. I think it's less than 600 observations. So you can see that unstructured will take a lot of memory to fit something. But it's probably a good idea to not use it if you can get away with it. All right, so for homework, take your data, fit some generalized estimation equations, and just compare the coefficients, see how they look different, see how they're, anything interesting about. Just explore, get used to this, and then keep this in your tool belt and, show me what you get and post it into Canvas. That's all I've got for you. Life is short. Do math.